going to introduce this in a little bit simple way. I mean, it's really kind of a stupid distinction, but if I'm doing things in a constant volume process, then the heat that's going in has a little V for it. So that's the heat that flows in a constant volume process. And you remember MCAT, so I'll just put here MC, and then I have to actually specify that it's a constant volume process because that changes specific heat. So let me label this thing specific heat. So I guess what I'm arguing is that, well, remember MCAT, there's going to be a delta T here also. So that is the heat that flows in a constant volume process, and this is the mass specific heat, or we'll just call it the specific heat. And then I can write this other equation that is annoyingly similar, but you'll be able to tell the difference of these. Look at that, isn't that cute? And this is a capital C, and then times delta T. So you'll be able to tell the difference between these two because this sucker doesn't have the same units. Creighton, do you remember what this N is, the little lowercase n?
The number of moles.
That's right, so that's the number of moles, and this is the mass. And this is the number of moles. And people may ask you test questions, certain people might ask you test questions that give you the molar specific heat, or they give you the mass specific heat, or the true specific heat, and they'd be happy if you could go at it either direction. So that's a little distinction that I needed to make before I go on. Let's go on. I want to distinguish constant volume. I want to distinguish energy storage, heat storage, right? I really want to get into the idea of a specific heat, distinguish energy storage and heat storage for constant volume versus constant pressure situations. Ready? Here we go. Here's the big question. I'm going to set it up with constant volume first, and I'll get a box. And the thing about constant volume is it's got a lid on it. So I've got this cylindrical box, and it has some initial temperature. And I'm going to note that it's a closed lid. There is no changing in volume, period. So that means I guess it's going to do no work, right? And then in the next situation, I'm showing, this is as time goes on, I'm going to show some heat going into it. I guess heat should be red, right? Heat goes into it, and as a result, well, what do you think will happen if heat goes into a closed container? What's going to change about it?
Pressure.
Absolutely, the pressure is going to change. And if the pressure changes, give me some PV is nRT. If the pressure changes, what else is going to change? What do you think?
What?
If the pressure changes, what else is going to change?
The number of moles.
What?
No.
I can't get more gas in here.
The volume.
Well, no, it's constant volume.
The temperature.
The temperature. So it's going to go up to some final temperature. And that's heat capacity. That's what it's about, right? I'm putting heat in, and I want to know how the temperature is changing. So in this equation, we can, in this situation, we can define heat capacity to be, well, it's going to be CV, and it's lowercase, but you can't really tell that. That's going to be the heat that went in constant volume. Oh, we should label that. That's the constant volume heat, that Q that goes in right there. And then, well, it depends on, let's use the molar one. You want to?
Yes.
Let's just use it. So this is actually uppercase. It's going to be divided by N and divided by delta T. I don't want this lowercase c or uppercase c to bother you much. But the reason we're using moles is because it's a gas and we don't want to have to measure its mass, so that's annoying. So we'll just measure its volume, 22.4 or something, and wave our hands around. But the next situation I want to explore is, put a little dotted line right here. The next situation I want to explore, let's see, this is volume constant. And the next one I want to explore is pressure constant. You know, one way to keep pressure constant would be to put a movable, frictionless piston on top of my system. So I'll do that, and the piston will be purple. There we are. And I'm going to put a mass on top of it. And that mass is going to help provide pressure for me. There's the mass sitting on top of the gas mass. And then I add some heat to the system. And as a result of that, well, guess what, Creighton? The piston's going to be rising. And that means that our system is doing work on the mass, right? And let's see, I was going to draw some heat going in here, and it's constant pressure heat. So instead of QV, I'm going to write QP. Oh, that's a terrible P. There, that's a little bit better. And our final situation is going to, it's going to include the mass being up higher, because the volume has changed, but the pressure has remained the same. And there's our mass. Sorry, it looks like the mass has been shrinking. There, now it looks like the mass has stayed the same. There's probably also some initial temperature here and some final temperature here. And we could again define an equation for constant pressure specific heat, or molar specific heat, whatever, and we'll write that as QP divided by N delta T. And Creighton, the most important question is this: how do these two relate to each other? And in particular, which one's bigger?
Which C is bigger?
Which of these situations, in which of these situations is the system more efficiently able to store energy? Because you know the bigger C represents an efficiency of energy storage. Which of these two is more efficient? Which of them can take on the most heat without changing its temperature quite as much?
The piston.
The piston. Brilliant. Your work here is done.
Thank you.
That's it. I mean, I guess that's all I said. What? No, let's get into it. Ha 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 ha. You want that?
Yeah.
Go ahead. I want to actually consider a, let me say one more thing before we go. The reason that Creighton is absolutely brilliant is because this gas is doing work in addition to just raising its temperature. This gas, all it's got is it's raising its temperature. This one is raising its temperature and doing work. So that work is another sort of dimension that it can store energy in. So it's storing energy in temperature and also in the fact that it has lifted up that mass by mgh, gotten some energy into there. So the next step is to examine a monatomic ideal gas. And our plan is, well, we've actually done a little bit of this already. We've kind of hinted at it. But our plan is to look at the heat flow there. Well, heat flow is simply change in state of the energy of the system, right? Plus the work done by the gas. So this is a weird way to look at it. I always like to look at it like this. The change in energy of the system is, well, the heat that would be going into it minus the work that the gas has done. So I'm just solving this equation for the heat flow. And then I'm going to go on and say that, well, in a constant volume situation, in a constant volume situation, I've got QV is delta U. Because in a constant volume situation, I've got that gas that's trapped and it can't do any work. There's no work term right here. So that's actually really simple. And the change in U, the change in energy, is just 3/2 nRT, as you'll recall from, what, 5 videos ago or something like that? So I can solve this for CV because I've got that other equation over there for CV. My equation for CV said CV was QV divided by N times delta T. And, oh man, that's beautiful. There's supposed to be a delta in here, isn't there? Of course there is. Sorry about that. So I'm going to because it's change in energy, of course there would be a delta. I'm assuming not changing the number of moles. So I'm going to say that CV, the molar heat capacity, then is simply 3/2 R. Huh. That's really simple. This is the ideal gas constant. And I'm taking 3/2 of that sucker. And that's my heat capacity for a constant volume situation. Creighton says, though, that a constant pressure situation is going to be a larger specific heat. So let's go into it. Constant pressure situation. We can start with the idea of work done in a constant pressure situation, because you know that work will not be 0 because it's lifting up that mass. That's one way of thinking about it. Pressure times volume is our work, and the pressure is constant, and this is going to be, well, it'll be the number of moles times R times delta T, because okay, very good. And then, do you like that? But the change in energy of the system, as we saw up here, is Q minus the work. So QP, the heat going into a constant pressure situation gas, is the change in energy of the system plus the work done by the system. And that's just, well, the change in energy of the system is going to be the same. It's going to be 3/2 nR delta T. That's the same as we saw for the constant volume situation. But then some work is being done, and it looked like that work was N times R times delta T. And then we're supposed to take this. Remember, if we're going to CP, I mean, in this case, we're supposed to take the definition of CP, which is QP divided by N delta T. And I'm going to take this stuff and divide it by N delta T. I'm going to get 3/2 R plus R. Why, that's just 5/2 R, and oh, dang! Creighton, look at this. Look. Oh, I can't use that color. What I'm saying is that CP is 5/2 R, and CV is 3/2 R, and just as you've said that CP is greater than CV. I'm going to say that CP minus CV is simply R. And you find that for certain gases like helium, nitrogen, oxygen, argon, carbon dioxide, it's not even a monatomic ideal gas. It's so far from all that stuff. All 6 of those gases, oh sorry, methane also. Methane? That's so much not a monatomic gas. Unbelievable. Anyway, all 6 of those gases are within 1% of CP minus CV being R. They're like 1.01 R or 0.995 R. Forget about it. This is incredibly powerful, ended up being way more useful than our initial assumptions. So all we need to understand is why the work done by the gas was nR delta T. Can you tell me?
Say it again.
Why was the work done by a constant pressure gas N times R times delta T?
Because it equals PV.
This is the ideal gas law. Wonderful. Goodbye. Actually specify that it's a constant volume process because that changes specific heat. So let me label this thing specific heat. So I guess what I'm arguing is that, well, remember MCAT, there's going to be a delta T here also. So that is the heat that flows in a constant volume process heat, or they give you the mass specific heat or the true specific heat. And they'd be happy if you could go at it either direction. So that's a little distinction that I needed to make before I go on. Let's go on. I want to distinguish constant volume. I'm going to introduce this in a little bit simple way. I mean, it's really kind of a stupid distinction, but if I'm doing things in a constant volume process, then the heat that's going in has a little V for it. So that's the heat that flows in a constant volume process. And you remember MCAT, so I'll just put here MC, and then I have to add the same units. Creighton, do you remember what this N is, the little lowercase n?
The number of moles.
That's right, so that's the number of moles, and this is the mass. And this is the number of moles. And people may ask you test questions, certain people might ask you test questions that give you the molar specific process, and this is the mass specific heat, or we'll just call it the specific heat. And then I can write this other equation that is annoyingly similar, but you'll be able to tell the difference of these. Look at that, isn't that cute? And this is a capital C, and then times delta T. So you'll be able to tell the difference between these two because this sucker doesn't have this